Operational amplifiers are usually characterized using this triangle, and this would be the output terminal. It has two inputs, and we usually indicate one as a negative input or an inverting input, and one is a positive input or a non-inverting input. The rails, or the supply voltages, are normally not shown on a diagram. This would go to a supply voltage on one side, and this would go to the supply voltage on the other side. The input signals are on these terminals, and the amplifier produces an output voltage which is equal to the difference between the voltage on the plus terminal and the voltage on the minus terminal, and the difference between them is multiplied by a number we'll call AV0. And the output then is proportional to the difference between the two input voltages, and this is done provided the input voltages are small enough. We're not going to talk about driving the amplifier into saturation. We're keeping everything in the linear region right now. And the voltage can be, the output voltage can also be written if we reverse the term in the parentheses. We can write it as V minus minus V plus. I give you exactly the same thing. So in either case, we have the gain AV0 is usually a very large number in magnitude. It tends to be typically about 10 to the 6th. So it's a very, very large number. And the difference between the two signals here is usually quite small in order for 10 to the 6th times a small number to give you something that is normally in the range of 100 volts or less. Most op-amps, the output voltage would be 100 volts or less. So you can see that although this is 10 to the 6th, this difference will be quite small, of the order of 10 to the minus 4 or even less than that in some cases. Now, these two voltages, which I will remove in just a minute, are called the rail voltages, and they are the power supply voltages needed to operate the op-amp. The range of V0, or the output voltage, is usually somewhere in this range. Let's say, for instance, this was up at plus 100, and this was at minus 100, and your voltage would range over this, go over the range of about plus 100 to minus 100. What is also fairly common is that we never quite go to the edge. So for instance, let's take out the 100 volt values. Let's suppose we're using 16 volts, minus 16 on this side. We normally will try to stay away from the 16 by stopping maybe say 13 or 14 volts. So there's always a room, there's always a bit of room left between the range of operation and the rail voltages. And this is to keep it linear. Consequently, we can write that V plus minus V minus, the difference between the two, is less than, in magnitude, the value of the supply voltage minus 3 volts, the whole thing divided by A sub V sub 0. So this keeps the voltage quite small in that range. For instance, if we were using 16 volts, as we did in our example here, if we use a value of, say, 10 to the 5th for AVO, then it turns out that the voltage difference in here would have to be somewhere around 0.13 millivolts. 0.13 millivolts. Also, the input impedance, looking into an operational amplifier, is usually quite high. Input impedances of the order of 10 to the 5th or larger would not be uncommon. And the input currents that flow into the op-amp are also quite small because, as you can see, if you have a high input impedance, the current will be very small. And this is true in order for the op-amp to remain in linear operation. So, for instance, in the example we quoted here a minute ago, if we allow 0.13 millivolts, the kind of voltage we have on these lines, then with this kind of an input impedance, the current would have to be the order of 1.3 nanoamps. That's just obtained by dividing the 0.13 millivolts by 10 to the 5th. So for most practical purposes, we will assume that a current flowing operational amplifier is very close to zero. And that's a very good approximation.